Welcome, everyone. Today, we're going to explore an exciting topic, Introduction to Classification and Logistic Regression. This presentation will cover the fundamentals, the algorithms involved, and some key applications in supervised learning. I'm glad you're here, and I look forward to guiding you through these important concepts. Let's get started. Welcome to the second slide, where we introduce the concepts of classification and logistic regression. First, let's talk about the categories of supervised learning. These problems are generally divided based on the type of target variable we want to predict. On one side, we have regression, which deals with continuous values like house prices or temperatures. On the other side, we have classification, which involves predicting discrete categories or classes, such as whether an email is spam or not. Now, a special case within classification is binary classification. This is when we only have two classes to distinguish between, like yes or no, true or false, or positive and negative. It simplifies the problem to just telling apart two distinct categories, which makes it easier to understand and solve. The focus of this lecture is on classification tasks, especially binary classification, because they are foundational in supervised learning. And to tackle these problems, we introduce logistic regression. It's a very popular and powerful algorithm that helps us predict class labels by providing a probabilistic approach. Instead of just saying, this is class A or class B, logistic regression gives us the probability of an instance belonging to a particular class, which adds a lot of flexibility and insight. So, to sum up, logistic regression is a key tool in our toolkit for binary classification problems, and understanding it is essential as we explore more advanced machine learning techniques. Let's start by talking about the IRIS dataset, which is a classic example in the world of pattern recognition. It was originally introduced by R.A. Fisher back in 1936 and has since become a benchmark for testing classification algorithms. Its significance lies not only in its historical value, but also in its simplicity and well-understood structure, making it ideal for educational purposes and algorithm testing. One of the reasons this dataset is so popular is because it's very reliable. There are no missing values, which means we can analyze it without worrying about incomplete data skewing our results. This reliability makes it a perfect choice for experimenting with different classification techniques. Now let's look at the features of the dataset. It includes 4 numeric measurements: sepal length, sepal width, petal length, and petal width. All these measurements are recorded in centimeters, providing a standardized way to compare different flowers. The dataset itself contains 150 instances, evenly divided among 3 different classes: Iris setosa, Iris versicolor, and Iris virginica. Each class has an equal representation, with about 33.3% of the data, ensuring a balanced dataset that's great for training and testing classification models. In summary, the IRIS dataset is a fundamental resource in pattern recognition. Its well-documented structure, balanced classes, and high data quality make it an excellent starting point for understanding and applying classification algorithms, including logistic regression, which we'll explore further in this presentation. Let's dive into how we approach classification and how logistic regression fits into this picture. When we talk about classification, we're essentially partitioning the feature space into different regions, each associated with a specific class. Imagine plotting the flowers based on their sepal length and sepal width. Each flower becomes a point in this two-dimensional space. This visual helps us see how the data naturally clusters. Now, logistic regression plays a key role here because it predicts the probability that a given point belongs to a particular class. These predictions translate into decision boundaries, lines or curves, that divide the space into distinct class regions. When we look at the visualization, we can see these clear clusters and the boundaries that separate them. It's important to note that classification isn't about predicting continuous values like in regression. Instead, we're focusing on identifying the regions where each class resides, whether a flower is of one species or another. This distinction is fundamental to understanding the nature of classification tasks. Finally, using the IRIS dataset, we get a great example of these concepts in action. The visualization clearly shows how data points form clusters and how decision boundaries can be drawn to classify new observations effectively. This visual insight helps us grasp how classification algorithms work in a real-world context. Let's start by looking at this example of binary classification. Here, we're trying to distinguish Iris setosa, which we label as class 0, from the other two classes combined. The goal is to use just the first two features of the flowers to predict whether a given flower belongs to setosa or not. Logistic regression helps us model the probability that a flower is setosa based on these features. It does this by learning what we call a linear decision boundary. That is, a straight line that separates setosa from the others in the feature space. This boundary isn't arbitrary. It's derived directly from the optimization process of the logistic regression algorithm. The model adjusts this line to best separate the classes, which leads to effective classification. What's important here is that logistic regression is quite powerful in binary classification tasks. It can create clear, interpretable boundaries, making it easier for us to understand why a particular prediction was made. And by focusing on just two features, we keep the model simple. This simplicity doesn't compromise accuracy significantly, but it does make the results much more understandable and practical for real-world use. So, in essence, this slide shows how logistic regression can effectively handle binary classification problems, providing both a straightforward decision boundary and interpretability, which are key advantages in many applications. Let's delve into some important limitations of applying ordinary least squares, or OLS, regression to classification tasks. One key issue is that OLS outputs are unbounded, meaning they can produce values outside the range of 0 to 1. This is problematic because, in classification, we interpret these outputs as probabilities, and probabilities must always stay within that 0-1 range. When the outputs go outside this range, it can lead to nonsensical results. Another important point is that the decision boundaries generated by OLS can be suboptimal. This means they might not accurately separate the classes, which can lead to higher misclassification rates. These shortcomings highlight the need for a different approach, one that constrains the outputs to valid probabilities. And that's where logistic regression comes into play. Logistic regression ensures that the predictions are always between 0 and 1, making them valid probabilities. Plus, it better models the inherent probabilistic nature of class membership. Instead of just trying to fit the data with a line, it explicitly models the likelihood that a given input belongs to a particular class. All of these issues, unbounded outputs, suboptimal decision boundaries, and the lack of probabilistic modeling, are what motivate the shift towards logistic regression. It provides a more appropriate framework for classification tasks by constraining outputs to be valid probabilities and ultimately improving the model's classification performance. Let's explore the logistic function, also known as the sigmoid. It's defined mathematically as sigma, z, equals 1 divided by 1 plus the exponential of negative. Essentially, this function takes any real number as input and maps it to a value between 0 and 1. This property is particularly useful because it allows us to interpret the output as a probability, which is crucial in binary classification tasks. When we look at how the function behaves at the extremes, as z approaches positive infinity, the logistic function approaches 1, and as z approaches negative infinity, it approaches 0. This means it smoothly transitions between these two bounds, making it ideal for modeling the probability of a binary outcome. Now, an important aspect of the logistic function is its derivative, which has a surprisingly simple form. Sigma prime of z equals sigma of z times 1 minus sigma of z. This simplicity makes the function very convenient for optimization in machine learning algorithms, as it simplifies calculations during training. Finally, because of these properties, the logistic function is perfectly suited for binary classification. It transforms linear model outputs into probabilities, enabling us to make clear, probabilistic decisions about which class an input belongs to. This makes it a fundamental component in many predictive modeling scenarios. Now, let's dive into the core of classification with logistic regression. At its heart, logistic regression models the probability that a given input belongs to a particular class. The key equation here is f theta. X equals sigma of theta transpose x, which is 1 divided by 1 plus the exponential of negative theta transpose. This may look complex, but essentially, it captures how the input features and the model parameters interact to produce a probability. Speaking of parameters, theta are crucial. They determine how the model responds to different inputs. Think of them as the knobs and dials that shape the model's predictions. By interacting with the features in X, adjusting theta changes how likely the model is to say yes or no for any given input. From a probabilistic standpoint, logistic regression isn't just about making a guess. It frames the prediction as a Bernoulli distribution. This means we're thinking of the output as a probability, an estimate of how likely the target is to be class 1, grounded in solid statistical reasoning. And finally, the output itself is a conditional probability. P theta, y equals 1 given. This tells us the likelihood that the target variable y is 1, given the input features. In essence, logistic regression provides a nuanced, probability-based view of classification, which is both intuitive and powerful for many real-world applications. Let's now delve into how we train logistic regression models using a method called maximum likelihood estimation, or MLE for short. The core idea here is to find the parameters that make our observed data most probable under the model. In other words, we're trying to maximize the likelihood of our data given the parameters. We represent our dataset as D, which includes pairs of inputs and labels like X, I, Y, I. The likelihood function, then, is the product of the probabilities of each label given its input, expressed as L theta equals the product over all data points of P theta, Y, I, X, I. Now, directly maximizing this product can be computationally challenging because multiplying many probabilities can lead to very small numbers. To simplify calculations, we take the logarithm of the likelihood. This is called the log likelihood. When we do this, the product becomes a sum, which is much easier to handle mathematically. The log likelihood is expressed as letter 2113, theta equals the sum over all data points of log p theta, y, I, x, I. The main goal of MLE in logistic regression is to find the parameters that give high probabilities for the correct labels. Essentially, we want our model to be confident in its predictions when they are right. This principle underpins the entire logistic regression training process. The likelihood function plays a crucial role because it measures how well our model explains the observed data. By maximizing this likelihood, we're effectively tuning our model to better fit the data. In summary, maximum likelihood estimation is a fundamental method for training logistic regression models. It guides us to the best parameters by ensuring our model assigns the highest possible probability to the actual observed outcomes, making it a key concept in understanding how these models learn from data. Let's explore how we can estimate the bias of a coin using some simple data. Imagine we have a series of tosses. H, T. Our goal is to estimate the parameter theta, which represents the probability of getting heads. The likelihood function for this data turns out to be L theta equals theta cubed times 1 minus theta squared. This makes sense because it's based on the probability of observing the specific sequence we saw. Now, to find the best estimate for theta, we maximize this likelihood function. Doing so, we find that the maximum likelihood estimate, or MLE, for theta is 3 divided by 5, which is 0.6. You'll notice this matches the proportion of heads in our data, 3 heads out of 5 tosses. That's a key insight. The MLE tends to align with the observed frequency. This example helps us intuitively understand how MLE works. It's a method for choosing parameter values that make our observed data most probable. In other words, it's about finding the parameter that best explains what we've seen. And it all comes down to the data we observe. The likelihood function is directly influenced by our data, and by adjusting the parameters, we aim to maximize this likelihood. This process helps us arrive at the most plausible estimate given the data at hand. So, in summary, this coin toss example illustrates how maximum likelihood works in practice, by using the data to guide us toward the parameter value that makes our observations most likely. Let's dive into the introduction to classification and logistic regression. The main learning objective here is to understand how logistic regression works and how we optimize it. At the core, the logistic regression objective is about measuring how well our model predicts. This is done using something called the average log likelihood, which is also known as log loss or cross-entropy. Think of it as a way to quantify prediction accuracy. The higher the likelihood, the better our model is performing. The formula for this involves summing over all data points, where for each, we consider the true label y, I, and our predicted probability sigma, theta letter 1d40x, I. This prediction probability is derived from the logistic function, which squashes any real number into a probability between 0 and 1. Now, this objective serves a dual purpose. It penalizes incorrect predictions, meaning if our model gets it wrong, it's penalized, and it rewards correct predictions when it's confident. This encourages the model not just to be correct, but to be confident in its predictions, which is crucial for reliable classification. Moving on to the optimization part, unlike some models, there's no simple closed-form solution to maximize this log likelihood in logistic regression. So, we use an iterative method called gradient descent. It helps us adjust our parameters step by step, gradually improving the likelihood until we reach the best possible fit. In summary, understanding this objective and the way we optimize it is fundamental because it ties together how we measure our model's success and how we improve it. Key themes that resonate throughout our exploration of classification techniques. Let's take a closer look at the gradient of the negative log likelihood. It is expressed as theta j, theta, equals sigma of theta letter 1d40 x minus y, multiplied by. This vector essentially shows us the direction and the steepness of the increase in the likelihood function. It's a crucial component because it guides us on how to adjust our parameters to improve our model. Next, we have the parameter update rule, which is fundamental to gradient descent. It involves iteratively updating our parameters theta by subtracting alpha times the gradient theta j, theta. This process ensures we move in the right direction, towards minimizing the cost function and improving our model's fit. Now, let's talk about the learning rate, alpha. This is a key hyperparameter because it controls how big of a step we take during each update. If it's too large, we might overshoot the optimal point. If it's too small, convergence can be very slow. Choosing the right alpha is essential for the gradient descent algorithm to work effectively and efficiently. Finally, this iterative process of updating parameters continues until the model converges. That is, until the parameters stabilize around values that maximize the likelihood. When this happens, our logistic regression model is well fitted to the data, providing reliable predictions. So, in summary, gradient descent in logistic regression involves understanding how the gradient guides parameter updates, adjusting those parameters carefully with an appropriate learning rate, and iterating until we've found the best fit for our data. Let's take a closer look at logistic regression, which is a supervised binary classification algorithm. Its main purpose is to predict outcomes based on input features, making it very useful for tasks like spam detection or medical diagnosis. The model uses a linear decision boundary, but what's special is that this boundary is created through the logistic sigmoid function. This allows us to separate classes in a probabilistic way, giving us not just a yes or no answer, but a probability of belonging to a particular class. Moving on to the objective function, the algorithm optimizes something called cross-entropy or log likelihood. This helps ensure that the model fits the data as accurately as possible. To find the best parameters for the model, we use an optimization technique called gradient descent. It's an iterative process that adjusts the parameters step by step until the model converges on the optimal solution. Finally, from a probabilistic standpoint, logistic regression is based on the Bernoulli distribution, which is parameterized by theta. This means it provides a solid probabilistic framework for classification, aligning perfectly with its goal of estimating the likelihood that a given input belongs to a particular class. All of these components come together to make logistic regression a powerful and interpretable classification method. Now, let's talk about some limitations of binary logistic regression. As the name suggests, binary logistic regression is designed for situations where we have just two classes. It cannot directly handle scenarios with more than two classes, meaning when k is greater than 2. This limitation means we need to look for alternative methods when dealing with multi-class classification problems. One common workaround is what we call the one versus all approach. Basically, we train k separate binary classifiers, each one focusing on distinguishing one class from all the others. So, for each class, we build a classifier that learns to tell that class apart from the rest. However, this approach isn't perfect. It tends to be less elegant and can sometimes be suboptimal. For example, it might lead to inefficiencies because you're training multiple models, and sometimes the classifiers can produce inconsistent results, making the overall classification less reliable. This brings us to a more principled solution, directly modeling multi-class probabilities. Instead of breaking things down into multiple binary problems, this approach allows us to handle all classes in a unified way. It's generally more robust and provides a clearer, more elegant framework for multi-class classification. Finally, extending logistic regression to handle multiple classes involves developing models that can predict the probability of each class directly. This approach aligns better with our overall goal, to build models that are both accurate and conceptually straightforward for multi-class scenarios. Let's now look at how classification and logistic regression connect, especially through the softmax function for multi-class probability output. When we have more than two classes, the softmax function helps us assign probabilities to each class in a way that's both intuitive and mathematically sound. Now, a special case occurs when the number of classes, k, equals 2. In this scenario, the softmax function simplifies to the sigmoid function. This is a key point because it shows the close relationship between softmax and sigmoid, especially in binary classification tasks. Next, let's talk about some important properties of the softmax function. First, invariance. This means that if you add a constant to all the input scores, the relative probabilities don't change. So the softmax is unaffected by shifting all scores simultaneously, which can simplify calculations and improve numerical stability. Another crucial property is that the outputs of softmax always sum to 1. This makes sense because we're dealing with probabilities, and probabilities must add up to 1, ensuring that our model's outputs are valid probability distributions. Now, the formula for softmax is quite straightforward. It's sigma z, k equals exp, zk divided by the sum of xpzl. Over all classes L from 1 to k, this formula calculates the probability for each class k by exponentiating the score for class k and normalizing by the total sum of exponentials across all classes. Finally, the softmax function can be seen as a generalization of the sigmoid function to multiple classes. It transforms a vector of real-valued scores into a probability distribution over k classes, which is fundamental for multi-class classification problems. Let's delve into softmax regression, which is a probability model used for multi-class classification. Basically, it models the probability of each class with the formula p theta, y equals k, e equals the exponential of transpose x, divided by the sum of exponentials of theta L transpose for all classes L from 1 to k here, represents the parameters that are specific to each class k. Now, every class in this model has its own set of parameters, which are crucial because they help compute the exponential term that determines class probabilities. Think of these parameters as the unique weights that shape how the model predicts each class. Moving on to the learning objective, the goal is to maximize what we call the softmax likelihood across our dataset. By doing this, we ensure that the model is good at predicting the true class probabilities for new data points. As for optimization, we use gradient descent, which is quite similar to what we do in binary logistic regression. It's an iterative process where we adjust the parameters step by step to improve the model's predictions. Overall, softmax regression extends logistic regression to handle multiple classes, and by understanding its parameters and optimization process, we're better equipped to build accurate multi-class classifiers. Let's take a closer look at how softmax regression can be applied to the iris dataset, which contains 3 different classes. This illustrates the model's multi-class classification capability, meaning it can distinguish among multiple categories rather than just 2. It's a really powerful tool for handling datasets with several classes, making it versatile in various real-world scenarios. Now, when we visualize the results, we see clear separation among the iris setosa, versicolor, and virginica classes. This visualization effectively demonstrates how well softmax regression can separate different categories, highlighting its effectiveness. If we look at the decision boundaries in the feature space, we notice that they partition the space into 3 distinct regions, each corresponding to one of the iris classes. This helps us understand how the model makes predictions by dividing the data space into clear, understandable segments. Finally, applying softmax regression to this dataset with 3 classes, the model outputs probabilities for each class. Instead of just giving a single prediction, it provides a probability distribution across all classes, which offers a more nuanced view of the model's confidence in its predictions. Now, let's take a closer look at the softmax regression algorithm, which is a key method for multi-class classification problems. Softmax regression is a supervised learning algorithm, meaning it learns from labeled data, and it's specifically designed to handle situations where you have more than 2 classes to predict. One of the important features of this model is that it uses linear decision boundaries, similar to logistic regression, but with a softmax output. This softmax component is what allows us to interpret the output as probabilities, giving us a clear idea of how likely each class is for a given input. The objective of the algorithm is to maximize the softmax loss, also called the multi-class log likelihood. This means the model learns by adjusting itself to assign higher probabilities to the correct classes, effectively improving its predictions over time. To train the model, we use gradient descent, an iterative optimization technique. It works by gradually updating the model's parameters to minimize the softmax loss, helping the model get better at predicting accurately. Finally, softmax regression fits into a probabilistic framework by modeling a categorical distribution parameterized by theta. This extends the ideas from logistic regression to handle multiple classes in a principled way, providing a solid foundation for multi-class classification tasks. Let's dive into some advanced topics now, starting with the concept of maximum likelihood theory and the assumptions we make about data distribution. One key assumption in machine learning is that our datasets are sampled IID, meaning independent and identically distributed, from some unknown data distribution, which we call p-data. This is a crucial point because it ensures that each example in our dataset is drawn independently of the others, and that all examples come from the same underlying distribution. This IID assumption is fundamental because it justifies using maximum likelihood estimation to fit our models. When we assume our data points are IID, we can rely on maximum likelihood to find the best parameters that make the observed data most probable under our model. It's a statistical approach that hinges on the idea that the data distribution remains consistent, allowing us to make effective estimates. To understand this better, consider an example where we sample noisy observations around a true underlying function. These observations are independent and identically distributed around that true function, illustrating how data generation often follows the IID assumption in practice. This example helps us see how, in real-world situations, data points are often treated as IID, which simplifies analysis and model fitting. Finally, it's important to recognize that assumptions about data distribution aren't just technical details. They're critical for the validity of our models. If these assumptions are violated, our predictions can become inaccurate, and the reliability of our models can break down. So, understanding and respecting the IID assumption and data distribution assumptions is essential for building robust, trustworthy machine learning models. Now, let's explore the relationship between maximum likelihood and KL divergence, which forms the theoretical backbone of classification methods like logistic regression. When we talk about maximum likelihood estimation, or MLE, we're essentially trying to find the set of parameters that make our model as close as possible to the observed data. But what's the mathematical justification for this? Well, it turns out that minimizing the KL divergence between the empirical data distribution and our model's distribution is fundamentally the same as maximizing the likelihood. This means that, by choosing parameters that maximize likelihood, we're also minimizing the difference between how our model predicts and what we actually observe. The KL divergence acts as a measure of this difference. It's a way to quantify how one probability distribution diverges from another. So, in essence, when we maximize likelihood, we're reducing this divergence, ensuring that our model aligns closely with real-world data. This connection is crucial because it provides a solid theoretical foundation for why maximum likelihood works so well in practice. It's not just a heuristic. It's grounded in the idea of making our model's probability distribution as similar as possible to the true data distribution, which is what KL divergence measures. This understanding helps us appreciate the elegance and effectiveness of these statistical methods in classification tasks. Let's dive into the maximum likelihood interpretation of ordinary least squares, or OLS. Essentially, OLS fits parameters by maximizing the likelihood of the data, assuming Gaussian noise. This means we're looking for the parameter values that make our observed data most probable under this assumption. Now, this approach actually unifies regression and classification within a common framework, namely maximum likelihood. When we maximize the likelihood, we're effectively minimizing the squared error loss, which is a core principle in regression analysis. So, maximizing likelihood and minimizing error are two sides of the same coin here. The likelihood function, p of y given x and parameters theta, is modeled as a Gaussian distribution with a mean of theta letter 1d40x and some variance sigma squared. This essentially quantifies how probable our observed data is, given specific parameter values. In terms of the model, we're expressing y as theta letter 1d40x plus some noise term letter 3f5. Here, theta letter 1d40x is our predicted value, and letter 3f5 captures the randomness or noise in the data. OLS assumes that this noise is Gaussian, specifically modeled as n0, sigma 2. That means the noise has zero mean and some variance, which reflects the spread or uncertainty in our data points. This Gaussian noise assumption is fundamental because it leads us to the likelihood function I just described. It ties the linear model directly to probability theory, allowing us to interpret the fitting process as maximizing this likelihood. Finally, understanding this likelihood perspective is key because it bridges the gap between classical regression and more advanced probabilistic models, including classification methods like logistic regression. It shows how, at a fundamental level, both approaches are about modeling the data's underlying probability distribution and finding the best parameters accordingly.